name is Xinhan. Today I want to share some of our research on the stochastic approximation of network reliability. This project is in the collaboration with Professor Robert Hui and Professor Xinhan.
You know.
Okay.
Let's try again.
Okay.
Yeah, okay.
Yeah, thank you. So the network reliability is defined as the probability that the graph is connected if the links in the graph is operational with probability P, but the node in the graph is always perfectly operational. Let's say this like in this graph, for all its link operational with probability P, and node always works. When the network reliability is defined as a probability that the graph is connected. So the network reliability can be expressed in a polynomial form, like this. The coefficient in the polynomial fi is defined as the number of sets of I links whose removal will leave the graph connected. Let's say an example here is a ring graph with 5 nodes and 5 links. For F0, if no links are removed, the graph will be definitely deconnected. So F0 is 1. And if we just remove one link, one of these 5 links, the graph will also be connected. So F1 is 5. But if we remove 2 links from the graph will be definitely disconnected. Then we get the reliability polynomial of this simple graph, and this graph is very simple. So computing its coefficient is possible, but for those graphs with a large number of nodes and many links, the computing the number of different hard set is an anti-hard question. To solve this problem, we proposed a stochastic approximation of the network reliability polynomial. So it's obvious that if a graph is connected, then the minimum degree of this graph should be larger than 0. Our main assumption is that if for those graphs is larger number of nodes n and high link density PL, if the minimum degree in the graph is larger than 0, it's almost sure that the graph is connected. Then the problem of computing the probability that the graph is connected become a problem of computing the probability that the minimum degree in the graph is larger than 0. And I will not give the mathematical derivation of the stochastic approximation here, and we can get a formula of the stochastic approximation like this: 1 minus phi 1 minus p to the power n, whereas phi d 1 minus p phi dz is a degree generating function of the graph. And let's see the performance of this stochastic approximation. These two figures shows the curve of the network reliability and as a function of operational probability P for both Barbar-Albert model with 200 node and different link density, and Arrow-Ringing graph model with 200 node and different link density, and Barbar-Albert model with 500 node and different numbers of edges per new nodes. And we can see that both for these two kinds of graphs, the result of the stochastic approximation is almost overlapped with the result obtained by Monte Carlo simulation. Which means that our stochastic approximation works very well for this kind of graphs. So the advantage of the stochastic approximation is that it's accurate for graph with a large number of nodes and higher density, and also it's depends solely on the degree distribution, which is very easy to compute. And the short back of the stochastic approximation is also based solely on the degree distribution. So if we don't, if we use some graph with more with small number of nodes and more link density, like the tree graph with 10 nodes and L links, we can see there is it shows a big difference between the stochastic approximation and the non-color simulation. So in real world network failure problem, not only the links fail, but also the nodes. So here is another kind of network reliability called the node reliability, where the links are always perfectly works, but the nodes operational with probability P. Not surprisingly, it can also be expressed in polynomial form like this. And here the coefficient Sk is the number of the sets of connected subgraph of J with K nodes. Also not surprisingly, this the problem of computing Sk is also a hard question. So we also proposed that stochastic approximation for the node reliability polynomial like this. And let's see the performance of it. We can see that also for the node reliability polynomial, the stochastic approximation works very nice. And also the advantage is it's based solely on the degree distribution is accurate. Okay, the short back is the same. It's not, it works bad for graphs with small number of nodes and lower link density. So now we know the concept of reliability polynomial and node reliability polynomial, and we have some very nice stochastic approximation of it. So what can we use it? So let's see a small application of the stochastic approximation and the reliability polynomial. So now if we have a graph J with 7 nodes and we want to enhance its network reliability by adding 2 links. So yes, for this very simple graph, we can try all the different kind of combinations of links and see which one improves reliability polynomial best. But also, if it's come to 1 million nodes, it's not doable. And this question is proved to be an anti-hard question. So solving the problem of improving the real reliability polynomial of a graph is anti-hard. But now we have the stochastic approximation. When we observing the stochastic approximation of both reliability polynomial and the node reliability polynomial, we can see that both of these two reliability polynomial is monotony increase with the term of 1 minus phi 1 minus p. And luckily, this term could be expressed in another form, which is here. And then the problem of optimized stochastic approximation of reliability polynomial becomes this. And this for this problem, we can get a mathematical value. I will not give much detail of how to we get the results. So the optimal result of this problem can be obtained by greatly adding links between nodes with lowest degree. Let's see how this it works. So if we have this graph and now we want to add in 3 links to improve the network reliability most. So then for first, we check all the degrees in this graph. We find that node 1 and node 3 has the lowest degree, and then we add a link here between these two nodes, and then we update our list and find node 1, node 5 has the lowest degree, and then we add one more link, and we do the same thing between 1 and 7. Then we get an optimal solution of adding 3 links to this graph to get a higher reliability for node. And this is how this greedy algorithm works, which is very easy. So, but for this, we just get the optimal solution of the stochastic approximation. But if it's real works for the real cases of adding Quillin's problem, let's see the result. Here is the performance of our algorithm. In these two figures shows the Monte Carlo simulation result of adding 500 links to a real world network in 3 different strategies. The first strategy is we randomly adding 500 links into the graph, and the second strategy is our greedy strategy, and another is we just adding links between the nodes with highest degree, and we can see that both for the reliability polynomial and node reliability polynomial, the strategy of adding links between the lowest degree increase the network reliability most. Which is like the green curve shows, and then if we just randomly adding links, it shows as the orange curve. Okay, so which shows that our strategies works very good for adding links in the real world network. Okay, so because of time, I just introduced a small part of our research. If you want to know more detail about reliability polynomial and this approximation, you can read our paper. We have submitted to the IEEE transaction network and the service